Hello everyone, welcome to the third video in my mini-series about gravity. This one is going to be about gravitational potential energy. It's a little lengthy, but I've tried to keep it interesting and I hope that you will enjoy. So what will you learn today? You will learn how to calculate the change in gravitational potential energy near Earth's surface using mg delta H. You will learn the general definition of gravitational potential energy and how to apply it. You will learn that gravitational potential energy is always less than or equal to zero. It is equal to zero for an object floating in free space. You will learn the connections between work, kinetic energy and gravitational potential energy. You will learn how to interpret force-distance graphs, and you will learn how to calculate escape velocity for a planet. Let's start out near Earth's surface. We have a weight here of 10 kilograms. If we lift this weight 2 meters up in the air, how much work have we done on the weight? Well, we know that work is equal to force times distance. The distance in this case is 2 meters, and the force acting downwards is the weight of the weight. So, we have that work is equal to mg, the force, times h, which is equal to 10 times 9.81 times 2 meters, which is equal to 196 joules. This change in gravitational potential energy is the work that we put in by lifting the object. So the weight has now gained 196 joules in gravitational potential energy that can be released by lowering it again. Here we have a different scenario. James is still standing beside the weight of 10 kilograms. And it's lifted 2 meters up in the air. As before, James will say that, okay, the work put into the object is mgh, it's 196 joules. But here we have James's friend, who is standing slightly below James, and from his perspective the weight is lifted 3 meters up in the air. So he will say, well, the work done on the object is mgh, 294 joules. How do we clear up this confusion? Well, we always write that the change in gravitational potential energy is mg times delta h. And the deltas are important. They just mean the change in gravitational potential energy and the change in height. And both James and his friend will agree that the change in height, the distance we lifted the object, is 2 meters. This is very important to keep in mind, that we always keep track of the change. Now keep in mind that this formula only holds near Earth's surface, because as we know, g can change dramatically depending on where we are in space. Never use this formula when you're working with objects in space, only use it when you're working with objects that are near Earth's surface. Now, just like with gravitational force, there is a more general formula for gravitational potential energy that doesn't only apply near the Earth's surface, but anywhere in space. And it looks like this. Gravitational potential energy is equal to negative gmm over r. And it looks very similar to the definition of gravitational force that we've seen earlier. You will notice that there is a negative sign here as well, and this is important for the definition and something we will come back to later. It's important to keep in mind as well that objects can still gain and lose gravitational potential energy, but the value of it will always be negative or equal to zero. The terms here are GPE, gravitational potential energy, given in joules. We have capital G, which is the gravitational constant. We have capital M, which is the mass of the parent object, like the planet. And we have lowercase m, which is the mass of the other object that we compare it to. And we also have R, which is the separation between their centers of mass. In this video, unless stated otherwise, the mass of the parent object will always be the Earth, and the mass of the other object, which we compare it to, will be James. This definition of gravitational potential energy implies that as an object moves infinitely far away from its parent object, for example if James moves infinitely far away from the Earth, James will have a gravitational potential energy of 0. Thus, a completely free object floating in free space is our reference point. This also means that gravitational potential energy will be always less than or equal to 0, and it is equal to 0 when the objects are infinitely far apart. This will be important and is something we will discuss more later. Let's start out with a simple example of how to apply this formula. Here we have James floating at a certain distance Ri away from Earth's center of mass. We know that his gravitational potential energy, using the formula we just saw, is given by negative gmm over Ri, where capital M is the mass of the Earth and lowercase m is the mass of James. Now, if we increase the separation between James and the Earth to Rf, we know that his final gravitational potential energy will be negative gmm over Rf. So, before we have the expression for GPEI, and after we have the expression for GPEF. We know that this change in gravitational potential energy that James experiences is the work that we put into James. And we know that this will have to be greater than 0 because it takes effort to move James further away from the Earth. We are working against the force of gravity. So, delta GPE is equal to GPE final minus GPE initial, which, plugging in the values that we have, gives gmm, and then in brackets 1 over Ri minus 1 over Rf. And we know that this expression within the brackets is greater than 0, because Ri is smaller than Rf. So the total expression is greater than 0, which means that the work we put into James is greater than 0 as required. And notice how this would never have worked out if we didn't have the negative signs in the definition. Now let's take a little more extreme example. If James starts out at the same distance from the Earth, Ri, but then he moves infinitely far away from the Earth, so that his gravitational potential energy final is given by negative gmm over infinity. This is equal to 0. So what do we have now? The change in gravitational potential energy is the work that we put into James in moving him from Ri to infinity. And this will be his gravitational potential energy final minus that initial, which is simply 0 minus gmm over Ri, which gives us gmm over Ri. So this gmm over Ri is the work required to completely free James from Earth's potential. It is moving him from a point, a certain distance Ri away from the Earth's center of mass, to infinity, where he is no longer affected by Earth's gravity. So we see that when we move James infinitely far away from the Earth, he has a GPE of 0. So we know that only a gravitationally unbound object has a GPE of 0. As soon as it's influenced by the force of gravity, it will have a negative GPE. Free objects are objects that are floating around in free space and are not affected by gravity from any other body. All other objects that are bound, they have a negative GPE, which means that they require positive work done to them to become free and have a gravitational potential energy of 0, just like we did with James. Now let's discuss the concept of force-distance graphs and how energy can transfer between kinetic and potential energy. Here we have a ball that's approaching a funnily shaped hill. And we also have a graph here that describes the force that needs to be put on the ball as a function of distance rolled to get it past the hill. What will be the work done on the ball at each stage? Well, we know that work is equal to force times distance. And the force is described in the diagram, and the distance is also described in the diagram. So the area under the FD graph, which is shaded green and red, will actually be the work done to the ball at each stage. So let's step this through together. We have at stage 1, we read from the diagram that the force applied is 6 newtons, and it's applied for a distance of 4 meters. So the work at stage 1 will be 6 times 4, 24 joules. The second stage, we have a distance of 2 meters, but the force applied is 0 joules because we're not doing any work against gravity. So the total work done will be 0 joules. Third stage, we have a force applied of 4 newtons times 2 meters, which gives us 8 joules. And the last stage, same as before, we have a force applied of 0, so the work done to the ball at this stage is 0 joules. So the total work that we have done to get the ball up here is 28 joules, the sum of all the parts. And these 28 joules of work that we put into the ball have now been converted into gravitational potential energy. So the change in gravitational potential energy from the beginning to now is 28 joules. Now keep in mind how elegant this is. All we have really done to calculate the work needed to get the ball up here is that we have calculated the area under the curve, which is simply two rectangles, its base times height. Now, what will happen as the ball rolls down the hill? Well, these 28 joules of work that we put into the ball that got converted into gravitational potential energy now get converted into kinetic energy. So, the change in gravitational potential energy is negative 28 joules because it loses all its height. But this is converted into kinetic energy, so it will gain 28 joules of kinetic energy as it rolls down. So now, when the ball has rolled down, it will have a certain velocity, which we can calculate using the 1/2 mv² formula if we want. And this interplay between kinetic energy and gravitational potential energy can simply be written as a conservation law. So we know that the change in kinetic energy plus the change in gravitational potential energy has to be zero. Energy doesn't appear out of nowhere. Kinetic energy and gravitational potential energy just get converted between one another. So we put work into the ball rolling it up the hill, and this work is now converted into kinetic energy again. And in absence of friction and air resistance, what an object loses in gravitational potential energy, it gains in kinetic energy. Here we have a graph describing the force that acts on James at various distances from the Earth. This graph just comes from the formula that we went through last week, which is the force due to gravity is equal to negative gmm over r squared. We start plotting at the radius of the Earth and go outwards, and you can see the second blue spot on the diagram is where James is currently. But this graph is actually itself a force distance graph. On the x-axis we have distance away from the center of mass of the Earth, and on the y-axis we have the force applied to James. That also means that the area under the curve between 2 points is the work done in taking James from, in this case, the radius of the Earth up to where he is now. So how do we calculate this area? Well, this is actually exactly the area that you're calculating using the formulae that we use when James was in space. So the change in gravitational potential energy, which is the area, is equal to the final gravitational potential energy minus the initial gravitational potential energy. So in this case, it's negative gmm over r James, where he is now, minus negative gmm over r Earth, the radius of the Earth, which simplifies down to gmm, 1 over r Earth minus 1 over r James. And this is the area, and this is the work that we need to do to take James from the surface of the Earth up to where he is now. We can take this further as well. So if we move James away an infinite distance from the Earth, this means that on the plot, the radius of James will be infinitely far to the right, infinitely far along the x-axis. What is the area here? What is the work done? Well, the area is the work done in taking James from the radius of the Earth away to infinity. And this is what we calculated before as well. The change in gravitational potential energy is the final minus the initial. The final, as we saw before, is just 0 because we're dividing by infinity, minus negative gmm over radius of Earth, which gives us gmm over radius of Earth. So this is the work required to completely free James from Earth's potential. Now we can ask ourselves an interesting question. If we have James infinitely far away from the Earth, and we let him fall back towards the Earth, what velocity would James have as he hits Earth's surface? Well, just like with the ball, James's change in gravitational potential energy in going from infinity down to Earth's surface will be converted into kinetic energy. And we know that the work needed to free an object from Earth's potential is given by gmm over the radius of Earth. We also know that kinetic energy is given by the formula 1/2 mv². So we now have everything that we need to calculate the velocity. So if we equate gravitational potential energy with kinetic energy, we have gmm over r Earth equals 1/2 mv squared. And the mass of James that appears on both sides, it cancels. And if we rearrange for v, we have that the velocity is equal to square root of 2gm over r Earth, where capital M is the mass of the Earth, g is the gravitational constant, and r Earth is the radius of the Earth. This of course ignores atmospheric effects such as air resistance. Now, it doesn't matter if we convert gravitational potential energy to kinetic energy by letting James fall down to the Earth, or if we start off by giving James a push, giving him kinetic energy and letting that convert itself to gravitational potential energy. Energy can transfer freely between these two forms. Therefore, an equivalent question we can ask is, how much initial velocity must we give James to make him just escape Earth's potential? How much kinetic energy do we need to give James for him to end up at a position infinitely far away from Earth? Well, the answer is exactly the same, because these two energy forms can transform freely between each other. This is called the escape velocity, and it's called that because it is the velocity that an object needs to escape Earth's potential. And interestingly enough, you can see that the escape velocity is independent of the object's mass. It only depends on the mass of the Earth and the radius of the Earth. So this means that whether we want to fire a rocket up away from Earth, or if we want to throw a little stone up, they both require the same velocity to escape Earth's potential. The escape velocity is independent of the object's mass. For Earth, the escape velocity is about 11,186 meters per second, which is a huge number. So that's the end of this video, and you should now know how to calculate the change in gravitational potential energy near Earth's surface using mg delta h. You should know the general definition of gravitational potential energy and how to apply it. And you should know that gravitational potential energy is always less than or equal to 0. It is 0 for an object floating in free space. You should know the connections between work, kinetic energy, and gravitational potential energy and how they can transfer between each other. You should know how to interpret and use force-distance graphs. And you should know how to calculate escape velocity for a planet. That's it for this video, and if you have any questions, please comment below and I'll respond to you, or you can save your question and ask me on Wednesday. See you next time!